Hello and welcome to Electricity Lesson 5. Today's lesson is on IV characteristics, or we might also call it IV graphs, so current voltage graphs. So quick recap, conventional current goes positive to negative and actual electron flow goes negative to positive. But what happens if we reverse the direction of a battery? So we take the battery out and we reverse it. Well, obviously, the direction of the current will be reversed. So conventional current here is going anti-clockwise. If we take the battery out and flip it round, then the current can go the other direction. In both cases, the bulb will still work, or whatever else is in the circuit will still work, but we reversed the direction of the current. This question comes up almost every single year in the exams, and unfortunately, about 50% of people seem to be getting it wrong when it's a really simple concept. You take the battery out, you reverse it, and you change the direction of the current. So what's the point of this? Well, supposing we plot on a graph current versus voltage, we can get a graph that looks like this. Now, for maths, you obviously know that graphs can have 4 quadrants, positive, positive, and negative, negative for the ones we're going to be interested in. So in this example here, we've got the current going, conventional current going anti-clockwise. So we're going to decide that is positive. No reason other than we're going to decide it's positive. We're going to plot it up here. If we reverse the direction of the battery, then we'll get the current down here. Now, later on in the lesson, you'll be able to say, hang on, Mr. Simon, there's something wrong with this slide. So hopefully you can spot what is actually wrong with the slide, because there's one very, very silly mistake that I've made. Now, one little point for you to read. So we're going to look at resistors first of all. So if you plot current against voltage for a resistor, you get this graph here. So what can you tell me about this graph? Pause the video for 30 seconds and write down everything you can think about this graph. So firstly, it's a straight line graph, but we can do better than that. A straight line through the origin means it's directly proportional. So voltage is directly proportional to current, which means that the value of resistance is constant. It's always the same. So if you take any two values, we know that resistance is voltage divided by current. So if you do voltage divided by current for these values, that will be the same as for these values, same as for these values, same as for these values, etc. So the resistance is always the same. So this is one of 3 graphs we're going to look at today. And here is the important information. I'm not going to say anything. You can read through it and make some notes as the points come up on screen. So you might have heard of Ohm's law before. I just really want to make the point clear. Resistors follow Ohm's law because they are special, because they have this straight line graph here. Ohm's law is not this formula. Ohm's law is that the line on a current voltage graph is straight if the temperature is constant. So resistors are special. Other things do not follow Ohm's law. So bulbs. Have a little think about this graph, write down everything you can about this graph now. So what can you tell me? Well, firstly, it's not a straight line. So it's not directly proportional, which means it does not follow Ohm's law. So for a bulb, something different is happening. Now let's have a little look here. We increase the voltage and the current increases a lot. This point here, we increase the voltage and the current increases kind of a medium amount. And at the top here, we increase the voltage a lot and the current barely increases. So why is that? Well, the resistance is increasing as we use a bulb. So when you actually turn a bulb on, it gets really hot. And when something gets hot, its resistance increases. So because its resistance increases, it tries to stop the current flowing. So as we increase the voltage, the current increases, it starts to get really, really hot about here. And the resistance increases, which stops the current flowing. So even though we're increasing the voltage, because the resistance is so high, the current can barely increase anymore. So if you take voltage here and divide it by current, you will not get the same resistance as if you do voltage by current here, as if you do voltage divided by current here, or voltage divided by current here. So lots of information there. I've summarized it for you on the screen now. So you can pause the video and make a few notes. The last thing I want to say is just to clarify point number 3, a small section might follow Ohm's law, but overall the bulb doesn't. So it might be that this small section in the middle, so just this little bit here is straight, and you might get a question, label the ohmic portion of the graph, or which parts of the graph follow Ohm's law, in which case you would maybe just draw on this small section here where it's straight, but overall it's clearly not straight. So overall it does not follow Ohm's law. And here you go, here's drawn on a line where maybe it does follow Ohm's law. Okay, the final thing we're going to look at today is this thing called a diode. So it's a new component that you might not have seen before. This is the circuit symbol for a diode, a circle with a triangle in. Here is another symbol for something very, very similar. You probably can tell me what this is immediately. It's a light emitting diode. The arrows point outwards to show that it's emitting light. And you get these all the time, different colors. They're really useful because they're really energy efficient. They barely produce any heat at all, which means they last a lot longer on the same battery than an old style light. And they're obviously better for the environment. You can also make them really small, so things like TV screens or computer screens sometimes use LEDs because you can make them really, really small. So they have lots of advantages. Now, what's special about a diode other than what I've said, other than being efficient, etc.? Well, they have a very special property, and it's actually shown with this arrow here. This arrow shows the direction that current can go through, and actually current can only go through this one direction, the way the arrow is pointing. If you try and go the wrong way, well, you just hit this wall here and you get stopped and you can't go past. So diodes only allow current to flow in one direction. We can show that on a graph here. If we have negative potential difference, we get zero current. The current is blocked. But even more interesting, if we have a small potential difference, again, nothing happens, the current is blocked. Then you only have quite a large potential difference, maybe 0.7 to 1.5 volts, then we get current flowing, and actually it rapidly increases here. So negative potential difference is zero current, small potential difference is zero current, larger potential difference is a rapid increase in current. Does this follow Ohm's law? Obviously not, because it's not a straight line through the origin. This bit here looks straight, but again, it's not, doesn't follow Ohm's law because it's not a straight line through the origin, so it's not directly proportional. So I've summarized everything I've said for you here, so you can make some notes now. The final thing related to this lesson. So we've looked at 3 components that you need to understand their graphs and explain why: resistors, bulbs, and diodes. You might also have questions where it's how do we investigate this? How do we actually produce a current voltage graph? So it might be a circuit like this, or it might be a slightly different circuit. This is one example. So what's in this circuit? We have a battery. So we have 2 cells making up a battery. The dotted line here just shows that we're connecting one and one cell together. We have a mystery component X. This could be a diode, it could be a bulb, it could be a resistor. And then we have a variable resistor here, an ammeter and a voltmeter. Why is there a variable resistor here? Well, this allows us to vary the total resistance in the circuit, which means we can vary the current and the voltage across this component, and we can vary the voltage and record the current. So we can get a graph of different voltages against the current, or different potential differences against the current. Why is there a switch? The switch makes sure the circuit does not get too hot in between us taking the measurements, which is very useful because you don't want it to heat up, because then that will affect the resistance. So you can now pause the video and complete the final set of questions.